All right, I want us to consider, maybe? Yes, I want us to consider the oxygen molecule for a second, right? And if we draw a good Lewis structure of what oxygen looks like, we will come up with probably this picture, okay? Double bond, four lone pairs, makes perfect sense. Sounds nice. From a valence bond theory perspective, this makes perfect sense. We're having everything overlap. We've got orbitals, blah, blah, it all works out. The problem becomes an experimental issue. If you take oxygen, liquid oxygen, and pour it into a magnetic field, the liquid oxygen itself is attracted to the magnetic field. That's what we're looking at in this picture right here. Okay. And because the liquid oxygen is attracted to the magnetic field, that means that that oxygen molecule is paramagnetic. Okay. And if we remember paramagnetic from when we talked about atoms, that means we have to have unpaired electrons. I wonder how Aquaman feels about being riding on his leg, but whatever. Okay. If we take liquid nitrogen and pour it in a magnetic field, it doesn't interact with the magnetic field. And so the liquid nitrogen itself is diamagnetic, which makes sense based on its picture. But the problem is oxygen doesn't make sense based on its picture. So if we want to understand the bonding in oxygen a little better, we need additional details to be able to figure that out. And what we're going to have to do that is we're going to have to invoke molecular orbital theory. Okay. Molecular orbital theory works in the same idea kind of as valence bond theory, in that in valence bond theory, we're combining and overlapping atomic orbitals to make new hybrid orbitals. In the case of molecular orbital theory, what we're doing is we're combining and overlapping atomic orbitals, and we're making molecular orbitals. And the difference is the molecular orbitals can cover more than one atom. And a lot of times molecular orbitals will cover the entire molecule, okay? All right, but it's going to follow that same quantum mechanical rule that we saw with valence bond theory, in that the number of atomic orbitals we put into the equation is the same as the number of molecular orbitals we will get out of the equation. Okay, our big difference here is that we're going to be doing what's called an LCAO, or a linear combination of atomic orbitals, and I will walk us through that so we can do it. Now, again, like with valence bond theory and molecular orbital theory, we're not going to be doing the quantum mechanical calculations. If you go further in your chemistry, physics career, you will probably end up doing that. For us, what we're going to do is we're going to look at it pictorially. We're going to hopefully explain some of the bonding stuff. We're going to get a good idea of how sigma bonds and pi bonds work and what things look like. And then we're going to realize that really we need all of these theories together to help us explain bonding in a well-rounded kind of way. Okay, but first let's dive in and figure out how this molecular orbital theory business works. All right, remembering we said that, orbitals are wave functions, so they have wave-like properties, which means if we have two waves or two wave functions or two orbitals that are going to interact with each other, then we have waves interacting. And so if we think about waves interacting, there's two main ideas that can happen. They can line up with each other, like this guy here. We call that in phase. The peaks and the valleys line up exactly, and they add together to give us a bigger and more exciting wave. Okay. Or they could line up opposite of each other, where the valleys and the peaks line up, but they don't line up with each other. They line up opposite of each other. I would call this out of phase. And if we add those together, we get nothing. The wave is gone because all the peak points canceled each other out. Okay, these graphics are just showing us kind of the same idea that we're talking about. But this happens with atomic orbitals to make molecular orbitals. Okay, this point that we're mentioning here, this node, is where that orbital crosses the axis and changes from positive to negative. And a node, remember, a node again is where we have our electron density is equal to 0. Okay, and there's no electron density there. All right, that's really all we want to say about that. Okay, so let's look at what happens with an actual orbital when we do this. And we're going to start off small, right? Let's start with hydrogen, just like we did with valence bond theory. Take two hydrogens and overlap them together, right? We're going to add the two orbitals together. And when we do that, right, every time we do this, remember, we're going to put two atomic orbitals in, we're going to get two molecular orbitals out. One of those is from adding them together. When we add them together, we get what's called the bonding orbital, and it literally adds them together, right? This is along the bond axis between the two nuclei, and we have added those together, okay? Because it's along the bond axis and between the two nuclei, this is a sigma bond, and because we made it with 1s orbitals, this is a sigma 1s, okay? Now, the linear combination means not only did we have to add them together, we have to subtract them from each other as well. So when we subtract them, what we get is we get an anti-bonding orbital. The anti-bonding orbital is always denoted by a little asterisk or a star. I call it star because asterisk is hard to say. This is still a sigma bond because a sigma orbital, I should say. The sigma orbital because it's along the bond axis and between the two nuclei. But if you notice, there's a node here, and there's a node in the middle that is breaking the bond. Okay, so this bond, the anti-bonding orbital breaks the bond, and the bonding orbital is making the bond. So we're making and we're breaking. Okay, now this works out well because of all the electrons we put into this are in the bonding orbital. So the anti-bonding orbital is empty. Let's take a stab at some. Oh yeah, these are all sigma bonds because their end-on overlap along the bond axis. I said that. I don't know why I made it pop up later. All right. When we look at this, if we put this on an energy diagram scale and compare it to the hydrogen atoms that are loose on their own, what we see, I hit a button. Hopefully you can, yeah, I'm not muted anymore. Okay, we're good. Sorry, I don't know what I did. It beeped at me and made me nervous. What we see is if we have, say, this is the energy of where the hydrogen atoms are, the bonding orbital is always lower in energy and the anti-bonding orbital is always higher in energy. And the reason the bond is forming here is because all of the electrons we put into this bond go into the bonding orbital, right? We're following Hund's rule and Aufbau principle, and we're filling from the bottom to the top, okay? So the electrons end up in the bonding orbital and the anti-bonding orbital is empty. So the electrons overall have a lower energy, which is what they're looking for, okay? I'm not sure why I said nodes and phases here. Yeah, so there's a node here in the middle, which means, oh yeah, that's right, phases, which means we're changing the phase, right? In the bonding orbital, we didn't change the phase. It's all one thing, it's all big one lump. In the anti-bonding orbital, one side of this is negative and one side of this is positive. And that's a mathematical negative positive, not a charge negative positive. It's just a mathematical number, okay? So when we're going to draw the molecular orbital diagram for these, we're going to draw, I kind of parallel with this, although we don't have to show the atomic orbital parts to it. So what we're going to do is draw this. This is our energy axis. You got to have that. Okay. We have made two molecular orbitals. One is lower energy, one is higher energy. This is a sigma 1s. This is a sigma 1s star. There we go. Now, the hydrogen itself has, each one has one valence electron. We have two, so that's two valence electrons. 1, 2, and we did it. Okay, this is what I mean by a molecular orbital diagram. Okay, we're going to expand on this and grow it as we do some stuff as we go through stuff. Okay, so that's hydrogen. Now, the nice thing about this is we can do this for anything we want to do. Okay, so if we're going to draw dihelium, let's draw dihelium. All right, same idea. Helium, as we know, is 1s2. Okay, so we're going to have our energy axis. We're overlapping 1s orbitals again. So we're going to get a sigma 1s and a sigma 1s star. Okay. And now let's think about this. We have two helium atoms, right? Because we're doing He2. Okay. Each one has two valence electrons, so that's 4 electrons total. You probably get what I'm smelling now. So 1, 2, 3, 4. That's what the helium molecular orbital diagram looks like. Okay. Something we can notice here is that now we have electrons in both the bonding orbital and the anti-bonding orbital. Remember, we said the bonding is making and the anti-bonding is breaking. So while this made the bond, this dude is breaking the bond, and there is no net bond. Okay. which means this, which means this thing is unstable. We could say this does not exist, right? Okay, so that's one thing we can learn about molecular orbital diagrams and molecular orbital theory. Electrons in the anti-bonding orbital cancel out the bonding character of the bonding electrons. Okay, so this gives us another route into thinking about bond order. Okay, oops, I guess I'll leave it there so I can leave it there. All right, so if we think about it, what we just did with our, I didn't even change the color. I meant to change the color. That's dumb. Okay, anyway, sorry. We just did dihelium. And when we did dihelium, notice what we're going to have to do is count bonding and anti-bonding electrons here. So we have 2 bonding electrons and 2 anti-bonding electrons. So when we do that, our bond order is going to be 1/2 of 2 minus 2, which is 0. 0 means our unstable or does not exist condition. Okay. When we're counting things this way, remember this is different than how we did it with a Lewis structure. With a Lewis structure, you can just count the lines in the Lewis structure and you're good. With molecular orbital theory, you have to have the orbital diagram and you have to count antibonding and bonding electrons and figure it out. But everything we do should have a number between 0 and 3. So if you get something that's not between 0 and 3, something is wrong. Either the calculation is wrong or the picture is wrong, and that's kind of a clue. Doesn't necessarily mean you're right. It just means you're, well, it doesn't, never mind. Just because that, I'll shut up. I should edit this, but I'm not going to edit. All right, so we should get something between 0 and 3. Remember, the bond order is going to give us relative length and strength and stability of all of the bond in general. Remember, the higher the bond order, the stronger the bond, the shorter the bond, and all that fun stuff. All right. The other thing we can get out of molecular orbital theory is it lets us explore molecules that we might not think exist, right? We did that with He2, right? We said, okay, if we could form this molecule, it's not going to form because it's 0. Okay. He2 plus, right, is going to be the same idea. We have a sigma 1s and a sigma 1s star. Remembering our He2 had 4 valence electrons, but this we lost 1, so this only has 3 valence electrons. And we have 3 valence electrons, 1, 2, 3. It looks like that. All right, what can we tell out of this? We can figure out our bond order by saying this is 1/2 of 2 bonding electrons minus 1 anti-bonding electron, or 1/2 of 1, which is 1/2. This has a bond order of 1/2. What the heck does that mean? Well, it means that it kind of could maybe happen to form a bond. It's probably not very strong, right? It's better than nothing, but it's not a whole sigma bond. Think of it this way. It's 2 atoms sharing 1 electron instead of 2, okay? But because it's higher than 0, it could possibly exist. It's a longer bond than a single bond, okay? But it's a shorter bond than having no bond at all, okay? The other thing we can look at and say is, oh, this guy has an unpaired electron, which makes it paramagnetic. Okay, so let's look at another one. Okay, if we go in the second period, right, we're just working our way through, right? We did H2, we did He2. Okay, then this is the same idea as what we just did. Okay, now in reality, all of the atomic orbitals combine together to give us pairs of molecular orbitals. Okay, so if we look at lithium, lithium has 1s2, 2s1. Okay, so if we're doing dilithium, which is what I'm going to do first, okay, then you're going to have a 1s overlap of 1s, so that's going to give us a sigma 1s and a sigma 1s star, and then you're going to have a 2s overlap of 2s, which is going to give us a sigma 2s and a sigma 2s star. But every time we do this, the sigma 1s and the sigma 1s star will always be full. Okay, so once we get into period 2, we really only consider valence electrons, which is technically what we were doing before, but the valence electrons were all the electrons. Okay, so here we can jump ahead and just say, well, this is a sigma 2s and this is a sigma 2s star. okay? And we can do that because the sigma 1s and the sigma 1s star are both full and they both cancel each other out. Dilithium then has one valence electron per lithium, and we have two lithiums, so 1, 2, and that's empty. What's our bond order? Well, our bond order should be 1/2 of 2 bonding minus 0 anti-bonding. Yes, we're showing our work. You don't have to show this much work, but this is a bond order of 1. You could easily say this equals 1 if that floats your boat. Okay. Yeah, let's do beryllium while we're here and look at that. And then we'll be on our way. All right, so again, we have to draw our energy axis. Same idea, sigma 2s, sigma 2s star. And Mr. Beryllium here has 1s2, 2s2, so 2 valence electrons times 2 is 4 electrons total. You get where we're going, I hope. 1, 2, 3, 4. Well, the anti-bonding cancel out the bonding, so this should have a bond order of 0. Let's prove it to ourselves. 1/2 of 2 minus 2 is 0. Okay. Now, our goal with molecular orbital theory is, can we do this kind of analysis for anything that contains 2 atoms that are in the second period? Okay. Well, we did lithium and beryllium. Once we get past beryllium, we have to start thinking about p orbitals, and p orbitals make things weird. So I have another video about when we're going to add p orbitals, but this is the gist of molecular orbital theory. Okay. Yes, come back for the next one and we'll add p orbitals to it and get a little bit weird and we'll be all good. Okay. Let me know if you have questions or need anything, and I'll catch you next time.